I don't know.
Yeah, that's wild, man. Sam Altman. We're gonna find out soon what it is. Maybe we will. Maybe we won't.
At the risk of asking something heretical on a Discord channel, how do you feel about Zoom? I've noticed that Discord is not especially good at letting people see text when the resolutions are different between presenter and recipient.
Huh. Yeah, I thought about Zoom in the beginning, but Zoom is just you start the meeting and then after the meeting it's gone. There's no channels to communicate after the meeting ends, so it just didn't make sense for something like what we're doing here. But I like Zoom. I like Slack too.
Okay.
Yeah, there's a bunch of good options out there, aren't there? I did notice that though, because Aditya was sharing his screen yesterday. He was sharing some code, and I couldn't see the code. You had to really zoom in. Are you not able to see my text when I'm sharing?
Yeah, I can see, but I think it completely depends on like lot of other stuff. I mean, like if your internet is not that good, then it might ruin it as well. So,
Yeah.
like, I mean, you can face that issue in Zoom as well. The problem with Zoom I've seen is like, so sometimes if your Zoom is not like proper, like internet connection is not good, when you share screen, you are completely like distorted when you talk.
Yeah.
So those two doesn't go in hand always really well. So
Yeah.
that's actually a bit like screwed up with Zoom.
Yeah, yeah. Hold on. I'm just going to hop down to the web development channel really quickly, let them know that we're getting started up here, and then we'll get started. Hey, what's going on? Are you guys here for the machine learning book club?
Yeah, I just saw the post thing. I just clicked on it. I didn't see that the machine learning channel doesn't show up
Oh, okay, cool. Yeah, just go up to, if you can't see the machine learning channel, just go up to the rules, click the green check mark, and all of the channels in the server should open up for you. Yep.
Underdog, and then suddenly the underdog itself goes away as like
I don't know what he's gonna do after that. Maybe he
I
makes
mean,
another
he
AI.
can like he won't have any problem with getting a job and all.
Nah.
I'm pretty sure like he can do something. He'll do something really great. But like, I'm just what's the future for open AI? I'm thinking that. I mean, obviously it's developers and engineers are going to be there, but like it depends on what the new CEO comes, what's his vision is, and what he'll do.
Yeah.
I mean, I wouldn't expect the same from Tim Cook when he joined after Steve Jobs. So I didn't expect that. So it's the same thing. Like after Sam Altman goes, like the one who comes, I'm not sure how much I'll expect from him.
Yeah, we'll see. We'll see. All right, let's go ahead and get started because we do only have an hour and 30 minutes for this here. And every single time this event ends, I'm always like, I wish we had more time. Um, I say that with everything I do though. There's not enough time in the
I
day.
think that we are going to have it for like Friday, Saturday, Sunday. So three continuous days, and
Yes.
it should be over.
Yes, yes. So for those who have been attending, who are new today, or I mean, who are return, we were doing it every single Wednesday from 6 to 7:30 Eastern Standard Time. From now on, we're gonna be doing it Friday, Saturday, Sunday, 6 p.m. Eastern Standard Time. So we're gonna get an extra 3 hours a week, which is good. Yeah, I felt like we were gonna finish the book in like a year and a half, you know. So this way, hopefully, we can finish the book in 3 months, and then we can move on to more advanced concepts in machine learning, like natural language processing or deep learning or something just more deep. I know O'Reilly has some pretty cool books that are also hands-on, just like this one. So yeah, it's exciting. But for those who are new, the way we do this is we move super, super slow. So I just want to put that out there right now. We want to make sure that everybody understands what we're talking about before moving on. If you haven't been here before, I record and post all the videos to YouTube, so you can feel free to watch the previous sessions to get caught up to where we are now, or you could just independently read the book. So where we are right now is we started. We really expect people to read Machine Learning Landscape, Chapter 1. I put that in the event description. just because that's going to give you basically a high-level overview of the world of machine learning. Everything you need to really just talk about it conceptually in these meetings. Now we're working through an end-to-end machine learning project. So that's chapter 2. And we're about 1/3 of the way done with it. I'll go ahead and just share where we are so far, and then we'll keep working through the book. And so basically, I'm reading the book line by line. The only time I'm not reading it is if I'm typing code. So I have my Google Colab. I'm going to be typing code. I hope everyone else is also typing code along. If you're like, hey, I want to code along, but I don't have a Python IDE coding environment, you could always go to Google Colab. Welcome to Colab, and then just create a new notebook. And then you can start typing along Python code that easy. And you could add comments as you're typing along. So it's really nice for typing code and taking notes as you go along. It's perfect for something like this. I was actually using PyCharm last week, and Aditya was like, dude, just use this. And I typed it out. I kind of just retyped the code that we did the last couple weeks, and it's so much easier. I could see why people use this tool, and it's really, really great. So I'm going to go over kind of like where we were, and then we'll start reading. And also there's times where we encounter words or phrases or concepts that, you don't understand or I don't understand. I'll stop and Google it. I'll stop and do research if I'm in the middle of it, and I'll let someone else continue reading if you want. And when I find out the answers, then I'll circle back and just share what I found, and feel free to do the same. Yeah. Does anyone have any questions before we get started? Exactly. So we have kind of like a core group that's been showing up every single week. And the problem with just expecting everybody else to read the book is that some people can't access the book. Some people just don't have the money to buy the book. Some people don't have the time to read, like they only have this 90 minutes. And so this ensures that people who can't access the book, can't buy the book, only have this time, are able to read the book with us. And everybody's on the same page instead of like everybody being scattered throughout the book, moving at different paces.
Well, if it's helpful, I mean, you can probably just look up this book with it's cool. I mean, it's kind of like pretty
Yeah. You got version 3 too?
no, I imagine they're all probably have more things
Cool. Does anyone else have any questions before we get started?
I do.
Hey.
Can you hear me?
Yes.
Okay, my question is this. I'm fairly new. Is this a book that I can get from like Barnes and Nobles?
Yes. Every Barnes and Noble I've been to has it, or you could order it off of Amazon.
Okay, I just want to make sure. I was going to do that tonight. 'Cause I'm new, so I would just be listening to you guys. But I just want to make sure I can get that ASAP. So, okay, thank you. I'll go buy it tomorrow.
Yeah, I use O'Reilly. Personally, it's $50 a month, but I like it.
I don't know how many pages are in
Mm. Yep. Yeah. Yep. So we're doing the 3rd edition here. All right. So I'll go ahead and just share the code that we've went over so far. The first thing we did in this chapter was we just loaded up some housing data. So we created a function called load housing data. We fetched it from GitHub and we loaded it up. This is the housing data right here. We have 20,640 different properties with different attributes: longitude, latitude, population, households, etc. Then I went and got the head, so you can see that just gives you a glimpse of the data, so you could see kind of what it looks like. Info, which is going to show you how many.
Hey Jim, could you share your screen, please?
Oh, sorry. Yes. There we go. Sorry about that. Yeah, so import the housing data, check out the data, see all the attributes for the data. This is the head, housing.head, housing.info, tells you how many of each there are. So you can see, like, for longitude, we have 20,640, but for total bedrooms, there's only data for 20,433. Counts for the ocean proximity. So you can see that you could kind of take a look at the data in different ways. And then housing describe, this starts getting into more statistical perspectives of the data. We used matplot for plotting. I believe these are called histograms. So we have histograms of the data, so you could start visualizing it. Then we created training and test sets. So if you're curious about training and test sets, feel free to do some Google searches and dig into that. We did some digging pretty extensively during our previous sessions. But basically, we're splitting into a training and a test set so that we could train our machine learning model. We need those. This was an inefficient training and test set split. This was a little bit better, but you're still building it manually. And then we used one from Scikit-Learn, where Scikit-Learn actually has this same method built into the library, and so you don't have to build it yourself because you don't want to recreate the wheel. This stuff already exists. So we went and split it into a training and a test set with Scikit-Learn. Then we looked at the income category, created 5 buckets. You can see most people are making are in the second and the third buckets. And then we went into a more complex version of splitting into a training and a test set. And feel free to search for stratified shuffle split. It's just a way that people split the data, but they're actually creating like multiple buckets of. You could create like 10 different training and test sets, so you could really just break down the data into a more granular level. Just did some more looking at the data. Here we created a scatter plot of the data, just looking at latitude and longitude and just looking at the income. So you could see, obviously this is the state of California. You can see that the income is like towards the ocean for the most part, except Sacramento. And then we did it again where we're changing the color. So the color is telling us what the median house value is, and the size is showing us the population. So the larger ones are the population. The smaller ones are places with smaller populations. And then the color is median house value. So the actual like median value of homes in that area. You can see they're super low here, and they're pretty high on the coast. And then right before we signed off last week, we visualized data again with a scatter matrix with median house value, median income, total rooms, and housing median age. We're basically just looking for patterns in the data, and I believe what we figured out was that there's a linear relationship between median house value and median income. Same here, median house value and median income. You can see the linear relationship. Yeah. And then I'm going to go ahead and, so we are right. Attributes, scatter. Yes, so we're right here. And then, so I'm going to start reading. Feel free to, if we encounter a word that you just don't understand, like looking at the correlation scatter plots, you're like, what the heck is a correlation scatter plot? You don't have to wait for me to be like, hey, people probably don't know what this is. There's some new people here. Can someone go look for it? Just if we encounter a word where you don't understand, just go look for it. Just go Google it. If someone else is reading and I encounter a word that I don't understand, I'm just going to Google it. Like if you're looking at my screen, you'll see me just doing research and typing code and that sort of thing too. So hopefully everyone's coding along too, so you could actually get your hands dirty and memorize this stuff and like let it stick. But besides that, we will go ahead. So the main diagonal would be full of straight lines if Panda plotted each variable against itself, which would not be very useful. So instead, the pandas displays a histogram of each attribute. That's this here, these ones here. Other options are available. See the pandas documentation for more details. So if you want to, feel free to dig into the pandas documentation. Looking at the correlation of scatter plots, it seems like the most promising attribute to predict the median house value is the median income. Like we said, we sort of realized that last week. So you zoom in on their scatter plot. I'm going to go ahead and type this code. Feel free to type the code along with us. And if somebody would like to start reading this paragraph right here, feel free to do that as I type the code. Most people are probably coding along though, so you don't have to.
I'm not coding, so I'll read it.
Yeah, do your thing.
So basically, we're just zooming in to the scatter plot. Is that what we're doing?
Yeah, we're zooming in. We see that there's a linear relationship between median house value and median income, and so we're basically just drilling in a little deeper into that.
Right.
Yep.
Are you ready?
Yeah.
This plot reveals a few things. First, the correlation is indeed quite strong. You can clearly see the upward trend, and the points are not too dispersed. Second, the price cap you noticed earlier is clearly visible as a horizontal line at $500,000, but the plot also reveals other less obvious straight lines. A horizontal line around $450,000, another around $350,000, perhaps one around $280,000. A few more below that. You may want to try removing the corresponding districts to prevent your algorithms from learning to reproduce these data quirks.
Jim, can you I missed some part about correlation code. I didn't do it, but I want to do it. So can you post the link of this Google Colab of the book?
You're saying O'Reilly?
Yeah, just the Google Colab link. I mean, where I can get the code.
Oh yeah. Hold on.
I just want to get that correlation part so that I can continue coding with where currently you guys are.
Yeah, this end-to-end machine. I think this is it right here.
Yeah, I think just posted it here. I just want to get that correlation part.
Mm-hmm. There you go.
Thanks.
Yep. I'm just running my code here. Feel free to keep going if you'd like.
Okay, the correlation coefficient only measures linear correlations. As x goes up, y generally goes down. It may completely miss out on non-linear relationships. An example, as x approaches 0, y generally goes up. Figure 2-16.
Sorry about that. Go ahead.
Figures 2-16 shows a variety of data sets along with their correlation coefficient. Note how all the plots of the bottom row have a correlation coefficient equal to 0. Despite the fact that their axes are clearly not independent, these are examples of nonlinear relationships. Also, the second row shows examples where the correlation coefficient is equal to 1 or negative 1. Notice that this has nothing to do with the slope. For example, your height in inches has a correlation coefficient of 1 with your height in feet or in nanometers.
Okay, so they're just saying like why each one of these different visualizations are classified with these numbers here. Yeah, so so this middle one is 0. There's like, okay, there's no pattern that we could see here, right? But then if it's a 1, then there's a total linear relationship.
Right.
Positive linear, you could say.
Yeah, correlation matrix does that for you.
I mean, yeah.
Okay, so if it's 0, there is literally 0 correlation. If it's 1, there's a 100% correlation.
No, you call it like one as a positive correlation and negative one as a negative correlation. So 1 means basically it is directly proportional and -1 means inversely proportional.
So as 1 goes up, the other one goes up if it's 1,
Yeah,
but
1.
as 1 goes up, the other one goes down for -1.
Correct.
Okay, that makes sense. And then, so these are different though. These look like, they're,
Looks like in 0 you can have like different shapes
Yeah.
at the very bottom. So
Yeah, I mean, so I think I don't know, like, so I think what that is, I think is basically a non-linear correlation in 0 and all. If you see, there was a parabolic curve as well. I think that's non-linear correlation. So this is like cubic curve.
No, it's saying they're decorrelated.
Oh.
0 indicates decorrelated.
So, okay, so what if there is a non-linear correlation? So it's still like
okay, so you're saying that we're only going to be discussing correlation if there is a linear relationship. Otherwise, we'll be using other language to discuss the patterns or the relationship. Because there's clearly patterns in this data here, but there's just no correlation. Yeah. Yeah, I'm gonna do a little digging later too. I just pulled up correlation in Wikipedia, so I like to always do a little bit more digging. I'll share what I learn here in the machine learning chat later on, either later or tomorrow. All right. So, experiment with attribute combinations. So hopefully the previous sections gave you an idea of a few ways you can explore the data and gain insights, which it definitely did. You identified a few data quirks that you may want to clean up before feeding the data to a machine learning algorithm. I think one of them is just this line here. If you look at this line, you can see that a ton of properties kind of just are all gathered here on this line, and that's definitely going to interfere with the model that we're building. I think we talk about that a little bit later. Let's see. You identified a few data quirks that you may want to clean up before feeding the data to a machine learning algorithm, and you found interesting correlations between attributes, in particular with the target attribute. You also notice that some attributes have a skewed right distribution, so you may want to transform them by computing their logarithm or square root. Of course, your mileage will vary considerably with each project, but the general ideas are similar. One last thing you may want to do before preparing the data for machine learning algorithms is to try out various attribute combinations. For example, the total number of rooms in a district is not very useful if you don't know how many households there are. What you really want is the number of rooms per household. Similarly, the total number of bedrooms by itself is not very useful. You probably want to compare it to the number of rooms. And the population per household also seems like an interesting attribute combination to look at. The population per household. Okay. You create these new attributes as follows. Okay, so it looks like we're actually going to use two attributes from our data set to create a new attribute. So we'll use the total rooms attribute and the households attribute to create the rooms per house. We'll use the total bedrooms and the total rooms to create the bedrooms ratio, and we'll use population and households to create the people per house. Okay, so this is more about mixing and matching attributes to discover new attributes that could potentially be useful for our machine learning algorithm. That's what it seems like. So I'm going to go ahead and type that out. Feel free to code along, or feel free to continue reading if you would like as well.
I guess I'll pick up where it says, hey, not bad. Hey, not bad. The new bedrooms ratio attribute is much more correlated with the median house value than the total number of rooms or bedrooms. Apparently, houses with a lower bedroom ratio tend to be more expensive. The number of rooms per household is more informative than the total number of rooms in a district. Obviously, the larger the house, the more expensive they are. I can't see.
All right, we'll just pause for 1 minute. Feel free to, if anyone is just curious about anything we've covered so far, feel free to comment on that. Feel free to ask questions, or feel free to just share something. Total rooms.
So correlation matrix is just some vector. Then we're using ratios.
Mm-hmm.
So I think it is preparing for like a linear regression model. So I mean, it looks like it, right? Because there's some linear relationship that we can see from the graph. So obviously,
Yeah, I think so. I think that's what I said. Like, so, let's say if there is some relation, some non-linearity being created between two variables, but for regression, like for a linear regression, you can make it linear by kind of scaling that particular variable in such a way that it becomes linear with the target variable. By example, taking log or something. So that's what I was saying when I raised the point about non-linear correlation. So sometimes it can be non-linear. Like, it's not like it won't be, because the correlation can show it non-linear. But like, you kind of scale that variable in such a way that it actually becomes linear.
right. So that was kind of probably the reason why we zoomed in into that graph to make it
Yeah.
link.
Yeah, to make the relation between the variables linear. Because if you bring in non-linearity, then it would affect the model, because then you cannot use linear regression model.
Right. That makes sense.
That's interesting. So the bedrooms ratio, the one that we just created, is much more correlated with the median house value than the total number of rooms or bedrooms. So we have rooms, total rooms, and total bedrooms, which are all 0.13, and then like 0.05, which is a small correlation. So bedrooms ratio is definitely more highly correlated. It's not a positive correlation, it's a negative correlation, but the correlation is definitely higher than basically anything. It's higher than anything except for median income. So by creating this right here, we actually created a piece of data with a higher correlation than any of the data we were given.
I think it's because like so I think the way it goes is like when two variables, the bedrooms and the total rooms. So that total rooms and bedrooms are kind of related. For example, like in one bedroom, like I mean in one room you can have like multiple bedrooms or something, right? So and that kind of like individually is affecting the total housing place, but also it was like affecting those two. Like there were like lot of mix correlation happening. I think this bedroom ratio kind of is handling that entire, because it's kind of like taking an average of combining the two factors like bedroom and rooms into one single factor. Now that one single factor, basically it's like every room, like there is a proportion between the number of bedrooms. So like the number of rooms and the number of bedrooms. So like even if there are like 10 bedrooms in one room and there are like one bedroom in one room, that ratio is going to give that proportion. And I think that's what is handling probably, making it linear.
Right. Right. Yeah. Yeah. When you said the factor being proportional to the number of bedrooms, and
Yeah.
yeah, that makes sense.
Okay, so as the median house value increases, let's just say we have a house with one bedroom and five total rooms, then the ratio would be 0.2. But if we had a room with five bedrooms and five total rooms, then the ratio would be 1. So as the median house value increases, the ratio of bedrooms to total rooms decreases. So there's actually less bedrooms per room per total rooms, right?
Yeah, but that's what the data tells. I mean, like
Mm-hmm.
basically it depends on what data tells. I mean, it's not like it's kind of like what the data which we have explains. That's what we can infer.
Yep. Yep. Cool.
It's
Cool.
like one thing which I learned about stats is everything is inference. It depends on how we infer data.
Mm. Mm-hmm. Yeah, or there's some kind of like, yeah, true. Or there's some type of like, you know, those neighborhoods with fixed pricing, like all the homes are the same value. Because it's not just 500,000 where I see a line. You could see a line at 450,000. You could also see a line at 350,000 and lines. Yeah. Yeah. True.
I think it depends on the data. So I think there would be some median like house ranges between house values between 400 and 500, but the data which we have doesn't have that. Like because I think the data suddenly like the data which we got, I think it kind of like doesn't have that cap, but there should be data. So I think like that 500 range would like affect the model, and I mean we need it to, because there could be some houses. I mean there would be some other parameters like the location, latitude, longitude, because the 500 range would be for those houses which are close to the coast. So they are anyways like the pricely houses. They don't depend on like, because the location also matters, right?
Mm-hmm.
So probably that 500 cap are for those houses. You can actually check like those 500 cap houses exactly what is the latitude longitude. I'm pretty sure they should be along the coast.
Yeah, definitely based on the previous one for sure.
Yeah, you can see like there won't be any 500 range like in between. They would always like coast is like the costliest. I mean, everyone wants
Yeah.
a beach house. So
Yeah.
I think that data would be needed. I think because that would make the model understand the prices at the coast as well.
So we're also saying that no matter how many of the houses and like we saw that 500 over there. So if we have like 1,010 homes, like we're also saying something about just building that would be used for each.
I mean, like it. So
See, there's like
like
14, right? Or
uh,
oh, never mind. Yeah, never mind.
All right.
So there are two things that I will remind you of. Last session, we looked at, there was a logarithmic transform on some of the columns, including number of rooms. So you can't interpret it as being like a 3-bedroom or a 4-bedroom house. You have to worry about its log of rooms divided by population, I think. And the other thing I'll remind you of is if you scroll up a bit, there was 9 histograms, and the last one shows a very, very strong spike at $500,000 median home price. So that bottom right, we have what's called a long-tailed distribution on home price. There are many homes that are of ordinary price, but there's a handful of mansions, and they're not being depicted here. They've been clipped in the data set.
Mm-hmm.
And that very strong spike of all the clipped data, that's also showing up as an artifact in the correlation that we're looking at, where there were several bands that it's popular to sell at 350K, but to sell it at $500,000 is extremely popular in this data set because anything that was above $500,000 is all lumped together.
Mm-hmm. Mm-hmm. And anything that's above 50 years old is also lumped together. Yeah. Okay, cool. Good to know. Thank you. Cool. So it's time to prepare the data for your machine learning algorithms. Instead of doing this manually, you should write functions for this purpose for several good reasons. This will allow you to reproduce these transformations easily on any data set the next time you get a fresh data set. You'll gradually build a library of transformation functions that you can reuse in future projects. You can use these functions in your live system to transform the new data before feeding it to your algorithms. And this will make it possible for you to easily try various transformations and see which combination of transformations works best. But first, revert to a clean training set by copying strat train set once again. You should also separate the predictors and the labels, since you don't necessarily want to apply the same transformations to the predictors and the target values. Note that drop creates a copy of the data and does not affect strat train set. So go ahead and do that right now. Cool. So clean the data. Most machine learning algorithms cannot work with missing features, so you'll need to take care of these. For example, you noticed earlier that the total bedrooms attribute has some missing attributes. You have 3 options to fix this. get rid of the corresponding districts. Let me just go ahead so everyone knows what I'm talking about here. When we did the details or info, you can see that longitude, there's 20,640, latitude, 20,640, housing, 20,640. But the total bedrooms is the one that's actually missing some. So that means there's no data for about 200 of the properties. And so like, what do we do with the properties where the data is missing? So one, get rid of the corresponding districts. So just get rid of those properties so they don't interfere with our data set. Get rid of the whole attribute. So just get rid of total bedrooms entirely, or set the missing values to some value. So set the missing ones to 0, set it to the mean or the average, the median. This is called imputation. You can accomplish these easily with the pandas, datas, frames, drop NA, drop or fill NA methods. So depending on the strategy you want to go ahead and use, we have option 1, option 2, and option 3 here. I'm not going to code this up until I see what we're doing. You decide to go with, okay. So you decide to go for option 3 since it's the least destructive. That makes sense. But instead of the preceding code, you will use a handy Scikit-Learn class simple imputer. So we're not going to use these handcrafted ones. We're going to use one that's built into Scikit-Learn. The benefit is that it will store the median value of each feature. This will make it possible to impute missing values not only on the training set, but also on the validation set, the test set, and any new data fed to the model. To use it, first you need to create a simple imputer instance, specifying that you want to replace each attribute's missing values with the median of that attribute.
So just to clarify, we're just basically giving more values to that column. We're just replacing it with like a dummy value, median.
Yeah, I think median makes sense because like it wouldn't have any variation, because if we add some data which will bring variation to the data set, then that is going to like change the model. So I think the reason it is going to the median value is because it won't bring up any variation to the data set.
Right. Okay.
It's still not an accurate representation of the real world, because the best would be to just have that data. But we're getting as close to an accurate representation of the real world as we can, right? With dummy data.
I think if you remove that data, if you drop those variables, I don't think there would matter so much, because I think the NA values are not too many. Like if the NA values would have been like, let's say 20% or something of the total data, then it would have been a problem, because you don't have data to train, so you need data. I think so here, like I think if you drop it, I don't think it would matter much to the model.
Because it's only 200 properties out of 20,000. Yeah, that makes sense. Since the median can only... Go ahead. Was someone going to say something? Since the median can only be computed on numerical attributes, you then need to create a copy of the data with only the numerical attributes. This will exclude the text attribute ocean proximity. Housing select, D types include, NP number. Perfect. Now you can fit the imputer instance to the training data using the fit method. housing num. Okay. So we have a simple immuter. And we're using the median. The imputer has simply computed the median of each attribute and stored the result in its statistics. So not only do we have access to the median for the bedrooms, we have access to the median for every attribute. Only the total bedrooms attribute had missing values, but you could not be sure that there won't be any missing values in new data after the system goes live, so it's safer to apply the imputer to all the numerical attributes. That makes sense, just so you have them if you're going to do it anyways. So let's check this out. Imputer dot statistics underscore. So okay, so it gives us the median value for longitude, latitude, number of bedrooms, all that stuff. And then we have housing num median values. All right, so we have our median values, and it's just stored in an array, as you can tell. Now you can use this trained imputer to transform the training set by replacing missing values with the learned medians.
Where does this transform function come from, actually? Is that from the imputer? Yeah, so
Yeah.
your object.
Yep. Yeah, so we're basically passing the data set into the transform method that comes with the Scikit-Learn class imputer. Yep. And then this will be our new data set, but this would be the data set with those missing values replaced with the median.
Right.
Yep. Okay. Missing values can also be replaced with the mean value, or with the most frequent value, or with a constant value. The last two strategies support non-numerical data. Okay, so whatever one shows up. Yeah, so if there's no way to convert it into numerical, or you just don't want to convert it into numerical data, then you would use the one that's the most frequent. For example, the ocean proximity one, if most of the properties are like less than an hour from the water, you would just use that one for the most frequent. So, okay, cool. And then a constant if you just decide to choose whatever one you think is the best. There are also more powerful imputers available in the Scikit-Learn.impute package, both for numerical features only. The KNN imputer replaces each missing value with the mean of the k nearest neighbors values for that feature. The distance is based on all the available features. Huh. Okay, that's interesting. That seems way better than just the median for the whole data set, because it's, yeah. Because then you're using the median value for the properties in the data set that are closest to this one. So using the median for the data in the data set, which is most likely to be similar or close to that one. Interesting. Okay. And the iterative imputer trains a regression model per feature to predict the missing values based on all the other available features. It then trains the model again on the updated data and repeats the process several times, improving the models and the replacement values at each iteration. Yeah, so these ones seem like they would be much more accurate than just choosing the median for the data set. Thoughts on that?
Right, so
Yeah, true.
Mm. Mm-hmm. Yeah. But then wouldn't the chance that there's an outlier be decreased because you're using the k nearest neighbors? So you're, instead of using the whole data set where you have like homes out in the country and homes near the water and homes in Sacramento and homes in Oakland, it would be using, let's just say we're looking at properties in Los Angeles who have missing bedroom data. Wouldn't it just be using the homes in that area, which intuitively, I feel like they would be less likely to have outliers if they're all coming from the same area, but I'm not positive. It's total speculation.
I guess that depends on what you're using to manage your operations. Like if you're using only lat long, that's a very limited implementation. But if there's other
Mm.
I think the way in this, like in the imputer which we are using, so I think in those imputers also there should be a function where you can fit and you can test if it is not affecting the data set, like the median or the mean values of the data set. If it is not bringing any variation, if it is not, then I think, like, I mean, you can test it and check, like, yeah, if it is bringing variation, means that is something wrong, because it shouldn't bring in variation to the existing data set, right? So I think just fitting,
That's
checking this.
categorically not true.
What?
Yeah, that's categorically not true.
Right.
As-
Right. Because we're using a stratified, like, training set, right? Is that why?
Yeah, we are using a stratified.
No, so imputation is making up data, and it's always going to have an effect. Suppose the two statistics that you're interested in are mean and median, and suppose that we have one of these very prevalent long tail curves, like we were looking at home price, which has a very long tail because mansions exist. And so, for a long tail curve, the median will always be below the mean because the mansions are elevating the mean, right? And if you impute with a median imputer, you're going to mess up one of them. If you impute with a mean imputer, you're going to mess up the other. It's just, that's how it is. You can't get away from it. You're making things up.
Oh.
That makes sense.
I mean, for housing statistics, I feel like, I mean, it also depends on what domain you're actually using, whether to use an imputer or just to drop the data, right? Like, I mean, like
Yeah,
if it's
yeah.
something with, like, let's say with some kind of like time series where you are basically observing a movement of a particular person as time goes. I think in those cases, if there are some null values, you can, I think, impute, because that wouldn't actually affect. But like if something like price, which basically depends on a lot of factors, not just like just one, or like just like you can see like it like it fluctuates a lot. So I think in those cases, using an imputer would actually affect. So it's better to drop the data, right?
as long I think it's like as long as your computer is trained on your training set, then it should be
Yeah, yeah. The regression imputer basically.
Mm. Cool. Thank you, everybody. So Scikit-Learn's API is remarkably well designed. These are the main design principles. Consistency. So all objects share a consistent and simple interface. They have estimators. So any object that can estimate some parameters based on a data set is called an estimator. So a simple imputer is an estimator. The estimation itself is performed by the fit method, and it takes a data set as a parameter, or two for supervised learning algorithms. The second data set contains the labels. Any other parameter needed to guide the estimation process is considered a hyperparameter, such as simple imputer strategy, and it must be set as an instance variable, generally through a constructor parameter. They also have transformers, so some estimators, such as simple imputer, can also transform a data set. These are called transformers. Once again, the API is simple. The transformation is performed by the transform method, which is what we used, with the data set to transform as a parameter. It returns the transformed data set. This transformation generally relies on the learned parameters, as is the case for a simple imputer. All transformers also have a convenience method called fit transform, which is equivalent to calling fit and then transform, but sometimes fit transform is optimized and runs much faster. And then we have predictors. So finally, some estimators, given a data set, are capable of making predictions. They're called predictors. For example, the linear regression model in the previous chapter was a predictor. Given a country's GDP per capita, it predicted life satisfaction. A predictor has a predict method that takes a data set of new instances and returns a data set of corresponding predictions. It also has a score method that measures the quality of the predictions given a test set and the corresponding labels in the case of supervised learning algorithms. Inspection. All the estimator's hyperparameters are accessible directly through public instances variables, so imputer.strategy, and all the estimator's learned parameters are accessible through public instance variables with an underscore suffix, so imputer.statistics. I believe we use that one too. Non-proliferation of classes, so data sets are represented as numpy arrays or scipy sparse matrices instead of homemade classes. Hyperparameters are just regular Python strings or numbers. Simple enough. Composition. Existing building blocks are reused as much as possible. For example, it's easy to create a pipeline estimator from an arbitrary sequence of transformers, followed by a final estimator, as you will see. And then sensible defaults. Last but not least, Scikit-Learn provides a reasonable default values for most parameters, making it easy to quickly create a baseline working system. Scikit-Learn transformers output numpy arrays or sometimes scipy sparse matrices even when they are fed pandas data frames as input. So the output of imputer.transform with our data set passed in is a numpy array. X has neither column names nor index. Luckily, it's too hard to wrap X in a data frame and recover the column names and index from housing num. It's not too hard, so we'll go ahead and do that now. Go ahead.
Yeah. So did we create a model? Like, because like when they mentioned hyperparameters, I mean, like that kind of like ringed a bell about like neural networks. Like, I don't know. I was just wondering.
I mean, hyperparameter tuning is also used in regression, right? Basically, I think
Right.
it's basically it's like it tunes the parameters in such a way that it basically aligns with the regression curve, right? Thing like that. So that
Oh,
way
right.
you tune the hyperparameters.
Yeah.
Yeah,
Yeah.
the last the ridge regression, last one the ridge, right? Those techniques.
Right. Because usually, and hyperparameter tuning usually implies that you're fitting or you're saying before you fit the model that these are parameters, and then you use like the standard parameters.
I think so. At the start, when the session started, like at the start, they talked about, I think, overfitting and underfitting. Is that where this comes into picture? Like to avoid like not too much variance and not too much bias. So that way you kind of try to use hyperparameter tuning, right? Or
Yeah,
regularization.
you're trying to find the sweet spot.
Yeah. Correct. Yeah.
But I guess the
because I was wondering if we already created like a model or something like that. But yeah, maybe
Create a model to predict like
I think they might have been talking about hyperparameters used in the previous chapter for like one of the explanations for yeah, one of the I'm pretty sure it was a linear regression model as well.
Yeah, I think for the model we don't. I think it's not about like for the model. I don't think this session is going to talk about hyperparameter. I think it's just to talk about because I think the input is also using a regression model. I think for that they are bringing up hyperparameter, but not for the model. I think.
right.
Yeah, I'm still not like too positive on exactly what hyperparameters are, but I'm eager to learn about it. You're right though, I don't think it talks about them here in this chapter.
I think you should read about overfitting and underfitting. I think that will take you to the hyperparameter tuning topic. So I think that's like where the concept starts. That why do you need hyperparameter?
I only know about hyperparameters. It just basically like solves the issue with underfitting and overfitting. Where you
Correct.
just,
Yeah.
yeah.
So if you know this concept, then I think so. If you know how bias and variance work, so you will understand that why do you need hyperparameter and what do you do for hyperparameter to control the bias and variance. If it's two variance, then that means like it's basically I think it's overfitting, and no variance means I think it's underfitting, and bias means I think it's over high bias. Oh, yeah, yeah. High variance means overfitting. It's basically trying to fit every point. So the curve, so yeah, there is low bias, and high bias means underfitting, where there's high variance, but like, yes, right.
Well, look at the model. It seems clear that the data was generated by a quadratic polynomial, and we decided that our model was going to be linear, which is not appropriate in this situation, but it's what we decided. That's where the bias comes from. It's about model choice.
Right.
But yeah, this might not be the for seeing the hyperparameters. You're using a linear model, spinning without like regular dimension.
Yeah. I think going for a non-linear model would make sense. Like, yeah, like a logistic model, like yeah, like a quadratic model.
Interesting. Huh. Okay. Cool. So handling text and categorical attributes. So far, we have only dealt with numerical attributes, but your data may also contain text attributes. In this data set, there is just one, the ocean proximity attribute. Let's look at its value for the first few instances. Feel free to keep reading if you would like to. I know we just had a short little discussion. Okay, so near bay. Okay, so it's basically just saying we have this many properties that match these descriptions here. It's not arbitrary text. There are a limited number of possible values, each of which represent a category. So this attribute is a categorical attribute. Most machine learning algorithms prefer to work with numbers, so let's convert these categories from text to numbers. For this, we could use Scikit-Learn's original encoder class.
Ordinal.
Ordinal, yes. What did I say, original? Pre-processing.
Wait, why are we using this? Is it? Oh, is this just okay, it's just an encoder. Yeah.
Mm-hmm.
Never mind. Yeah.
cool. So instead of near bay, we have 3. Instead of less than 1 hour to ocean, we have 0. Okay. So it's basically just giving a numerical representation to our categorical data. You could get a list of categories using the categories instance variable. It's a list containing a 1D array of categories for each categorical attribute. In this case, a list containing a single array since there is just one categorical attribute. Ordinal encoder categories. Okay. Cool. One issue with this representation is that machine learning algorithms will assume that 2 nearby values are more similar than 2 distant values. This may be fine in some cases for ordered categories such as bad, average, good, and excellent, but it's obviously not the case for the ocean proximity column. For example, categories 0 and 4 are clearly more similar than categories 0 and 1. To fix this issue, a common solution is to create one binary attribute per category. One attribute equal to 1 when the category is less than 1 hour from the ocean, and 0 otherwise. Another attribute equal to 1 when the category is inland, and 0 otherwise, and so on. This is called one-hot encoding because only one attribute will be equal to 1 hot, while the other will be 0 cold. The new attributes are sometimes called dummy attributes. Scikit-Learn provides a one-hot encoder class to convert categorical values into one-hot vectors.
Why do we need one-hot encoding?
It's just to represent the binary like relationship between like each attribute category. So like if it's like yeah, what the name implies, like 1. If it's hot, then it's hot. If it's cold, then 0.
Okay.
I think it's so with the ordinal coding, you're establishing so like it has you're pretty much saying like this variable has
Yeah.
if you go from like below average, above average, then there's something that order. But if you don't have like if these categoricals don't have ordering to it, then the one hots are just gonna allow each of them to be kind of like an on-off switch.
The model learns in that way if you give ordinal, and it might give you a bit different results than what is it. That's why, right?
It's like it's more of like a clear cut thing. It's like I think it's like like you only want to use ordinal if there's some actual order for that category. But
Yeah.
not
Yeah. Right. I mean that's what I'm saying. So like if you give it a like not one or hot encoding, then it would basically the model would like learn it in such a way that there is a order, which is not.
right.
So, yeah.
They would learn like or it might be there, but they're not connected.
True. Yeah.
By default, the output of a one-hot encoder is a SciPy sparse matrix instead of a NumPy array. Yeah, that makes sense because, yeah, for example, if we had like very bad, bad, average, good, very good, it's like the distance between bad, very bad, and bad is the same as from bad to average. Like the space between them are even, but the one hot encoder is gonna more accurately represent categorical data where there's not like a clear distance between the two categories, right? Yeah, okay. Cool. A sparse matrix is a very efficient representation for matrices that contain mostly zeros. Indeed, internally, it only stores the non-zero values and their positions. When a categorical attribute has hundreds or thousands of categories, one hot encoding, it results in a very large matrix full of zeros, except for a single one per row. In this case, a sparse matrix is exactly what you need. It'll save plenty of memory and speed up computations. You could use a sparse matrix mostly like a normal 2D array, but if you want to convert it to a dense NumPy array, just call the toArray method.
So I have a question. I'm like a beginner, right? And I'm transitioning from the learning network engineering stuff for my CCNA right now. So uh, I'm following along, trying to. Would this book be too advanced for a person who's just trying to like learn Python, or do you think I could like slowly pick up on things?
Oh, you could definitely slowly pick up on things. We're kind of I say we move through it slow, but I guess for someone who's like brand new, who's never done Python or any real software engineering, it is a little fast because there's a lot of things that we would have to unpack. But if you get the book and you start working through the book, just like slow way down and just Google things as you encounter them. Like if you're like, okay, I understand the concept, but I don't know what NumPy is, and I don't know what a NumPy array is. Like just Google it. You can slow down obviously if you're working through it yourself. Python is such a simple language that I haven't worked with Python either. I'm just picking it up by working through this book. But if I could go back and start over, I would definitely start with Python. So if it's definitely the language you want to start with, in my opinion, if you're just starting off. Yeah.
Because my goal is ultimately right to get my foundational skills in network engineering, but I kind of wanted to, after going to a couple meetups, like jump into like machine learning and AI. I know I might have to take a couple more math courses, like some calculus courses, just to kind of get the mathematical understanding of it. But I just wanted to jump into this course. I saw it. I was like, you know what? I'm gonna try to do something I've never done. So I appreciate you for slow poking for.
Yeah, for sure.
Yeah, you can definitely like pick up the concepts too, like from just listening to us discuss, because like it's just from experience, just like keep at it,
Mm-hmm. Mm-hmm.
One thing actually which helped me was like actually reading about statistics. There are like a lot of concepts which are like statistics concepts. Like
Yeah.
so like I had taken a course on statistics, and I kind of got aware of those concepts. And because of that, it's very easy for me to understand like when you actually do those operations. What is overfitting? What is underfitting? Why do you need those parameters? Why do you need hyperparameters? It's like it helps to understand the concept.
Yeah. Yeah, you said like calculus, and then also I know machine learning is linear algebra heavy, but honestly, the more I dig into it, the more I see that it's like 90% statistics. That's what it seems like, at least so far for me.
Well, yeah, that's cool because I did some research, and they were like, "Oh, you got to look at calculus and linear algebra."
Mm-hmm.
Like you said, I took statistics. I had to take statistics to get to my master's program. You have to have statistics before you can do network engineering. So I was like, "Oh, this kind of looks like statistics a little bit," but some people told me it was more so like linear algebra and calculus.
I think till now what we have done is basically EDA. That's the term which I've heard. So exploratory data analysis. And that's what we are doing like till now.
Yeah, we just do both like data prep, and there are
Yeah, I mean,
Bruce, what is your favorite language? Bruce, other than English, what's your favorite language?
Oh, okay. Um, well, right now I've been looking at Python. Are you talking about speaking or are you talking about like coding? Because I
I
actually
was
am
willing to
learning.
accept anything, but I was kind of driving towards computer languages.
Okay. Well, coding. I've been looking at Python for a long time because I want to get into scripting. But when I started studying for my CCNA, it was too much to try to like dive right into Python and do Neil Anderson's course on Udemy. So I've been pretty adamant with like learning dynamic routing protocols. But as I went to a meetup probably about 2 days ago about AI, some of the guys were telling me like, if you can get Python scripting down, you could actually like make a new lane for yourself. So I just been diving into that, and that's why I saw you guys on Meetup, and I was like, hey, I want to join that. It looks intimidating at first. I'm not gonna lie. It's a lot different than like configuring dynamic routing protocols like RTP, I mean RIP and OSPF, but I'm down to learn.
Excellent. So I was looking to see if you're already familiar with some other language. If Python is your first language, I agree with the sentiment previously expressed that Python is a terrific learning language. You should dive in with Python first, and you can later branch out as you wish. You're really going to need linear algebra for ML. If you don't know about matrix multiply and dot product, then there's a big chunk of ML that's sort of inaccessible to you.
Okay, understood. I was gonna look at Udemy and look at see if I can take some courses on it. But I mean, I could go to university, right? Take a course for like $300, but I figure Udemy is like $20 maybe at most to like take a course. So I figure that might be like an easy way to learn.
Honestly, you can learn linear algebra for free, like on Khan Academy. Like that's like literally how I first learned it, and then yeah, go from there. It's absolutely for free. So
Python is
Okay.
for the most part, you don't
Like
linear
I
algebra
never.
is even like when you get to more complex stuff, it's not going to be as constant. It's going to be like 1 or 2 semesters to really get everything. You probably need immersive to get completely through it. It's like unless you start to go into complex algorithms, you need to branch out
Yeah, I mean, on the things you learn, and really, I just kind of went through like, you know, basic tutorials, object oriented, and then I got the hang of it pretty easily. You just kind of got to really like understand definitions, and I've been using Python for I don't know how long, and it's really straightforward. I've done a little bit of machine learning. I was able to follow along with those books, and I know Python really well, and I know a good amount of machine learning. It's actually like starting to make more sense. Everything like we kind of went through today. And I've already, I kind of just like watched a few YouTube videos on it, but I've been doing Python for a really long time. So I think it's the best language to learn from the beginning. Like it's super easy. Once you get Python, you'll get everything else to it.
yeah, agreed.
Yeah. Thank you. I appreciate the empowerment. Definitely. I just Googled Cloud Academy, so I'm gonna get on that tonight. I work night shift law enforcement on the side, so I do night shift law enforcement. So I'll try to get in with you guys when you guys have your thing. Some days I work, but I work night shift law enforcement 7 p to 7 a. So I usually come home and do my studying in the morning for like 2 hours, knock out. But I'm definitely gonna get on that.
Yeah, I've been doing Python for like 8 years or more, than that, and like I've been doing it on the job, like, and it's definitely it's the easiest one to like learn. There's a lot of C plus so I would start off with Python. Once you get Python down and you get like the basics in there, it's like okay, yeah, this is so easy. It's like it's really easy. Like at this point, I've been working with it so long. It's just like I really like I could do anything. I'm done. And trust me, you'll get to that point where it's just like, oh yeah, like machine learning. yeah, I guess I'll make a focus on giving into
Cool, cool. Well, it's about 7:30 right now, so we will hop off. Feel free to hang out and just chat as long as you'd like. I'll be hopping out in a minute. Does anyone want to say anything before I take off?
Yeah, thank you, Jim. Thank you for going through this book for us. So thanks.
thank you.
Yeah, thank you.
Yeah,
Thank
I
you
went
very
through, yeah, thanks a lot. I went through I've gone through a little bit of machine learning and I was able to follow along, so everything is starting to make a lot more sense. Kind of doing the foundation, so it's definitely really interesting.
Awesome, awesome. Thank you all for coming.
I just want to say, like, I was gonna spoke about like some like doing these from scratch, just like tier cap, really helps out a lot, especially like beginner or
Cool, cool.
Right.
Alrighty.
Thank you.
Have a good one, everyone.